Okay, so we're going to start to talk about cell potential and spontaneity today. And before we start that, I need to review with you oxidation reduction, just to make sure you remember that. So up here in the top, and by the way, I'm sorry about the shadows; they're making me crazy too, but I can't get rid of them. So all right, so up here at the top, let's just review that by saying like oxidation. Do we remember what that is? We had a little acronym for it. Remember, Leo goes Gur. Okay, so that was Leo. So oxidation is lose electrons. Lose electrons. So an example of that is going from like 0 to +2. So it's getting more positive. All right, so that's oxidation. Losing electrons, you get more positive because remember, electrons are negative. And then reduction is Gur. Remember that was our little thing because Leo goes Gur. And Gur is gain electrons. That's reduction. That's what it stands for. And so that would be something like +2 to 0. It's getting more negative. Doesn't have to be actually negative, but it's going lower. Okay, so that's being reduced. Okay, so to be able to do what we're looking at now, this electrochem stuff, you have to be able to remember oxidation reduction. So now let's look down here. So we're trying to figure out, we'll have a scenario where there'll be something called a cathode and an anode. And the cathode is where the reduction happens. And the way you can remember that is red cat. So red cat is reduction occurs at the cathode. That's what it stands for, red cat. So just remember that. Anox is oxidation occurs at the anode. Okay. Oxidation occurs at the anode. And then fat cat is just telling us which way the electrons flow. So the electrons flow from the anode to the cathode. Okay, so I'll write that out. That's how you remember that. Electrons flow from the anode to the cathode. And you guys should have seen a setup of that from looking at the Edpuzzle that we had, like a setup of an anode and cathode. Okay. All right, so let's take a look down here at some other terminology they have. So cell potential, aka EMF. EMF stands for electromotive force. You don't necessarily have to know that, but I'm just telling you like what that is. So electromotive force. And we're trying to be able to measure the push and the pull of electrons in a galvanic cell. That's what the cell potential is. Do the electrons flow easily, or do they have to be pushed in a certain direction, and how much does that take? And so that's what that we're measuring. And the way you measure it was with something called a voltmeter. And if you've ever studied physics, they do some electricity stuff as well, and they use voltmeters as well. You can see the units for the volt and how you convert it from a joule and another different unit, a coulomb. That's just a nice conversion thing for you there. So E cell, and this is standard cell. That's what that's telling you right there. That's what it stands for. Is cathode plus anode. And I'm going to show you how I look at that as well. This right here, it says must be positive to be spontaneous. So this value here, when you calculate it, if it's positive, it's spontaneous. Now, we haven't talked about spontaneity yet because we went in a different direction because we had to do electrochem before thermochem because we have our field trip. But spontaneity is, I'm just going to put, it means that delta G has to be negative. And delta G is Gibbs free energy, which I promise we'll do notes on that soon. But if this is negative, this has to be positive for this to be negative. Okay, so that's just a relationship that you're going to have to know. All right, so to find oxidation from reduction, flip the reaction. Here's what that's talking about. So like you'll have a table, and if it's a question on the AP exam, they'll just give you the values. But these tables here are the reduction potentials. So if you're trying to find the oxidation, I think it says right here, if you're trying to find the oxidation from the reduction, you just flip it. So if you were trying to find, so you can see, let's look at it right here. So you can see that this this fluorine is going from 0 to -1. So it's being reduced, right? So this is the reduction potential. So if we needed the oxidation potential, we would just flip the reaction and then this would become negative. Okay, so that's all that. That's what that means. So you have to pay attention to what's supposed to be happening in your reaction. And we'll look at an example, which is where we're going now. The more positive the value, so if you look at these values here, the more positive it is, the more likely it is to be reduced. Okay, that's what that means. So let's take a look at some different reactions here. So let's label our oxidation numbers first. So remember, if the element's by itself, it's 0. And so these guys are 0, oxidation number. You can see it here, it's +1. These are nice and easy. And this is -1. So the hydrogen is going from 0 to +1. So what would you say is happening to it? I'm just going to put it over here. Hydrogen is going from 0 to +1. So I would say it's being oxidized. And then the fluorine, F2, is going from 0 to -1. So it's being reduced. Okay. And so we already have these, again, these guys here are the reduction potentials. So we can use the reduction potential for who? We can use the reduction potential for fluorine, which is literally the first one we looked at there. It's that 2.87. So the reduction potential for fluorine is that 2.87. So I'm going to put here E cell. And and let's label our cathode and anode real quick. So we set up here red cat. So reduction happens at the cathode. So this is our cathode, and then there's our anode. So that's that now labeled. Sorry, those are overlapping. And so up here it says cathode plus anode. So our cathode we just said would be, looking at that chart again, 2.87. And I gave you a handout of that too, so you hopefully have that. And then we're going to add the anode, but we have to flip it. So we're looking at hydrogen. So let's look at the list here. Let's see what hydrogen is. Oh, and as I see hydrogen is this one that's boxed, and you can see it's 0. So we don't have to really do anything to flip it. We're just going to say +0 because a -0 is 0. And we were going to say the E cell is 2.87. And that would be volts. And the thing about that is, going back to up here, is since this is positive, we would then say that this is spontaneous. Which all that means by saying it's spontaneous is it happens on its own. Like you don't have to do anything to make it happen. Okay. Happens without adding or doing anything to it. Okay. All right. So if you can, pause this and try the second one. Okay, so I'm going to give you a second to pause it, and then I'm going to do the second one. Okay, so let's look at the second one. Same thing. We're going to give the oxidation numbers. So manganese is 0, nickel's +2, manganese here is +2, and nickel is 0. So manganese goes from 0 to +2, and nickel goes from +2 to 0. So that means nickel was reduced. That means manganese was oxidized. And now let's figure out who's the cathode and the anode. So red cat, so our cathode is nickel, and our anode is manganese. Okay. So the one that, again, these things up here on the chart are reduction potentials. So whoever was reduced, you use that value like normal. So our reduction was the nickel, and it matters that it's nickel. It goes from nickel +2 to 0. So let's look at our sheet here and see if we can find nickel +2 to 0. So it's down here. You can't see it. Hold on. It's lower on the sheet. I just lost it. Where is it? Right here. Okay. So there's nickel. It's going from nickel +2 to 0. So it's -0.23. So we're going to put that there. So we're going to say E cell equals -0.23. Okay. And then we're going to add And then we're going to look at who else are we looking at? We're looking at manganese. So manganese is going from 0 to +2. So where's manganese on here? So see here, the one we have is manganese going from +2 to 0. So we need to flip that. So we're going to make that a positive 1.18. So plus 1.18. Okay, and we get that out and we add that, and I'm going to get 0.95 volts. Again, this is a positive value, so I'm going to say it's spontaneous. Okay. All right, so now we're going to be actually drawing a galvanic cell. Okay, and so but first we got to write the reaction for this. So it says, write the overall reaction for 2 balanced half reactions for zinc metal reacting with copper 2+. Identify the cathode and the anode. So we have zinc, I'm going to put here Zn, it's a solid, plus, it says copper, so that's Cu2+, and that's aqueous. Okay, and the zinc, we know that zinc likes to go to a charge of +2, so that's what's going to happen to it here. And that now is aqueous. Plus, and then the copper then is just going to go to copper solid. Okay, so that's our reaction. So that's just one more step because we didn't have the reaction like we did up here. So now let's label who's oxidized and who's reduced, and who's the anode, who's the cathode. So zinc goes from 0 to +2, and copper +2 goes from +2 to 0. So copper is reduced, and zinc is oxidized. And so the cathode is the copper, red cat, and the anode is the zinc. All right, so we're going to set that up like that. So then it says it wants us to draw the actual setup. So we're going to have in a galvanic cell, we're going to have 2 beakers. Okay. And we're going to make one side the cathode, one side the anode. And we're going to put a piece of, I'm going to say this is copper. I'm going to say this is zinc. Just label them. And we have to have what's called a salt bridge. A salt bridge is what enables our electrons to flow. Because without the salt bridge, we'd have a voltage of 0. So it says here that the salt bridge is potassium nitrate. So that means I'm going to have KNO3 here. Okay. And we have to indicate which ways, so when we have a salt bridge, you have K plus and we have NO3 minus. And one of them will go one direction and one will go the other to balance out the charge. So in our solutions, we're going to have, this is going to be copper nitrate. And this is going to be zinc nitrate. Okay. So those are aqueous, stuff floating around there. And we said the flow is from remember back up here, it says the flow is from the anode to the cathode. So who is the anode? We said the anode was the zinc. So that means our flow of electrons is going this way, flowing from the anode to the cathode, just the way I put it. Now, you didn't necessarily have to put that, like the zinc on this, the zinc over here and the copper over here. You could have flipped those, and then your flow would be that way. But it's always from anode to cathode. So we know that zinc was our anode, and we know that copper was our cathode. So that's why it flows from the anode to cathode. So showing that. Let's see. We started out with, what else do I need there? Oh, I guess we can calculate our E cell. We didn't do that, right? Okay. So that's here. So our E cell. If we look up, remember we're doing the cathode first. So the cathode for ours is copper 2+. So I'm just looking at my paper here. Sorry, I gotta find it. So I swear it takes me 5 years to find things on here. Okay, so copper 2+. And okay, so be careful because like this copper here is copper 2+ going to copper 1 plus, but here it's 2 plus to 0, which is what we want. So that's 0.34. Okay, plus, and then we need to look at the zinc, and we're going to have to flip it. So zinc is, I only look at these tables like once a year, so it takes me 5 years to find things on here. Where is the zinc? Oh, here it is, down here. Okay, so there's zinc, and zinc is going from +2 to 0, so that's good. That's what we want. But then we have to flip it because, again, this is our reduction potential, and it's being oxidized. So let's look at that. So let's, what did I say? In 0.76, right? So 0.76 goes here. So if I add that together, my E cell is 1.1 volts. And again, it's spontaneous. So that means this galvanic cell will run without me doing anything to it. Okay, and let's pause right here because we haven't talked about Gibbs free energy yet, except for me talking about it's being spontaneous. So I'm going to wait, and we'll start when we start the next section on thermo. I will talk to you about this. So pause for this part. And let me see if we can do the other notes on that. I think, yeah, so let me, I forgot to do a copy of that. Oh, here. Here we go. Is this what I wanted? This is what I wanted. Okay, so let's switch to this page, which should be the back of your page there. All right, so the question says, why would we want a spontaneous cell? So a spontaneous cell means it happens on its own. And so something like that would be, we want to do to make energy. I almost want to put to make usable energy, but whatever, that's fine. And the example of that is like a battery. Okay, so we can make energy. And then why would we want a non-spontaneous cell, the one that we want to make it happen? And this is for stuff like, we would use this for electroplating. I know you're thinking like, what is that? I'll tell you in a minute. For electroplating. So for an example for electroplating is like, I have it in my kitchen here. I could go grab it and show you. But when we want to put like a metal on top of another metal, we want it to like deposit on top of there. That's what electroplating is. So for example, I would put like copper on a tea kettle. So the tea kettle is not pure copper because that'd be really pricey. But sometimes we like plated stuff. So that happens in jewelry, again, in things we use in the kitchen, in pots and things like that. So I'm going to put copper on tea kettle because I drink tea every day. So I'll put that. And then I'm also going to say I'm putting like plating gold on jewelry. Gold and silver. They put them on top of it sometimes to make it cheaper. Okay, so these calculations here, and again, this little schematic is nice to be able to look at two different type of electrochemical cells. Galvanic also has another name. The other name for galvanic cells is voltaic. That's interchangeable, so I just want to make sure you guys realize that. And then electrolytic cell. So the spontaneous here, so that means that E cell, oh, it's down here. E cell has to be positive and delta G has to be negative. So that's what I was talking about before. And you'll look also, we have the K value for equilibrium has to be greater than 1, which makes sense. It's going to go in the forward direction on its own. Okay, so I just wanted you to be able to see like the various types of cells here. Okay, so down below here, and I believe this is given on the AP exam, we have, actually, I don't know if this is, but this conversion is. So current in amp, 1 amp, the way you calculate that is the charge in coulombs, that's Q, over the time in seconds. So we just divide those. And then we have a unit here. There's 96,500 coulombs is equal to 1 mole of electrons. This is also known as Faraday's constant. Okay, just something to know there. Okay. And then let's take a look at, we have a electrolytic cell here. And so this is a non-spontaneous. We haven't done these yet. And we're going to write down what's happening. So it says determine the reaction that happens with electrolytic cell when potassium iodide is electrolyzed. Complete the drawing along with determining the voltage needed in the battery to run this reaction. So I'm going to do this first one, and then actually I'll probably do the first two, and then I'll leave the last one for you so you can see if you can get it. Okay. And then we can check it in class. Okay, so we're going to set this up. So we have Ki, and it's aqueous, and it's non-spontaneous, so we have to add energy to it. Okay, that's what that is. And when we do that, it makes it become potassium plus iodine. We know iodine's diatomic. Okay, so we have to break this up into two half reactions. So what are the two half reactions happening? So this in solution, if it's aqueous, this is going to be K plus, and it's becoming K. So to make this equal out, I need, well, and we didn't balance this yet, actually. So let's go back and balance this. I'm sorry. So we have two I's over here, so we need 2 here and a 2 here. So this is going to be 2K, and then this is going to be 2K. So to balance this out on this side, I'm going to need 2 electrons over here. Right, if I'm trying to balance it, because it's like, where did that charge go? Okay, and then the other part, I have 2I minus, arrow I2, and over here, I'm going to put 2 electrons to balance that as well. And that's what that looks like. Okay, so if I look at so who's oxidized and who's reduced? K goes from +1 to 0. So K is reduced, and I is oxidized. Okay. So red cat, so this is the cathode, and ox, so this is the anode. Okay. So the reduction potential we can look at is the potassium. Let's see if we can find that. I'm going to look it up in this table again that I have trouble keeping track of. Okay. Potassium, ¿dónde está? Oh, it's down here at the bottom. Okay, so potassium is negative 2.92. That's what I saw. And then when I look up iodine, I get that it's, I should have kept it over here. Iodine is 0.54. We have to flip it, so negative 0.54. Okay, so my E cell, then I'm just going to add those. So E cell equals negative 2.92 plus a negative 0.54. And any math people probably hate that I put plus negative. And that equals negative 3.46, which confirms it's non-spontaneous because this is negative. Remember, because it has to be positive to be spontaneous. Okay, next question. So this one's a little different because it has a time involved, and we haven't had anything with time involved here. And it's giving us the cathode and the anode, and it's even giving us the reduction potentials. So let's take a look at what we have here. So it says a current of 10 amps is delivered to an electrolytic cell for 15 minutes. How many liters of hydrogen gas can be created from potassium iodide solution at 1 atm and 25 degrees C? So these values, these values are STP, standard temperature and pressure. You know what? I'm sorry. It's not. It's standard pressure. It's not standard temperature. Just kidding. Standard temperature is 0 degrees Celsius. Just disregard that. It's standard pressure. So we need to remember that amps is a coulomb per second, which we have it up here, like the unit. And it told us that we have 10 amps, and we're trying to solve for the coulombs, but it says 15 minutes. And if I calculate 15 minutes, that should be, 900 seconds, right? Because this is just times 60. Okay. So if I solve for coulombs, I'm going to get 9,000, right? Just multiply these guys. So I'm going to get 9,000 coulombs. All right, now it's asking me, I need to be able to get to moles because it's asking me about liters. And I know if I have liters and so I have volume, I have pressure, and I have temperature, I know I'm probably going to be using the ideal gas law. some point here towards the end. But to get to the ideal gas law, I have pressure. We're asking for volume. I know R, that's my constant, and I know T. So that means I need to be able to solve for moles. Well, the only thing that had moles in it, if I go back up to the top here, moles was in right here. I have moles in that conversion factor. So I've got to convert my coulombs to moles. Okay, so that's what I'm going to do right now. So I've got 9,000 coulombs, and it says 1 mole of electrons is equal to, up here at 96,500 coulombs. So now my coulombs are gone and I'm left in moles. Okay, but if I look at my reaction, which we have here, how many electrons do we have in our reaction? So they both say it's 2. So I need to do it for, I have 2 moles of electrons for every 1 mole of hydrogen. So that's what I'm looking at here. I'm looking at that, this right here. Every 1 mole of hydrogen has 2 moles of electrons. So I need to include that. So when I calculate that, I get 0.04663 moles of H2. So that's fine, but the question didn't want moles, it wants liters. So let me plug in my pressure, 1 atm. My volume we're looking for. My N is 0.04663 moles. My R, we know from back in the day, is 0.0821. My T is 25 degrees Celsius, but I got to change it to Kelvin. So 298, because I got to add 273. And I'm going to solve for V. So my V I solved for is 1.14 liters. Okay, try the last one, and we can check it in class.